is our video on exponential and logistic functions. So we'll start off talking about what an exponential function is. So if we have an exponential function, it's written f of x equals a times b to the x, and we have to have a be a non-zero number, and it was told up here before we started that a and b are non-zero real number constants. A is not 0 and b is positive, and b does not equal 1. So this is what we define to be an exponential function. Then we can have variations of exponential functions that can have different transformations like we've talked about, shifted right or left or flipped over, things like that. But when we say an exponential function, we do mean that we have the base positive and not equal to 1. So the base b here is positive and not equal to 1. And the constant a is the initial value. So this is what happens when you plug in 0, and b is called the base. So those are just some words that you can fill in there on your notes. And those are the important terms that we need to have so we can speak the same language when we talk about exponentials. Okay, so we're going to look at these different examples and decide if they're exponentials. And if they are, then we'll talk about the initial values and the base. So the first one, f of x, is 2 to the x. So that's definitely an exponential. And the initial value, which is the a, is 1 here because you don't write times 1. So it's a 1 in front, and the base is 2. So the base being what you're raising to the power. The second one is not a rational function. So we're not going to put an initial value or a base because it's not a rational function, or it's not an exponential. So this would just be, no, this is a rational function. And it's rational doesn't look like it the way it's written, but remember this would just be 4 over x cubed. A negative exponent means just move down. So this is a rational function, not an exponential. And then on the next one, h of x, this is an exponential, and you have an initial value of 5, and then your base is 2. You just happen to have a minus x for the exponent, which is just a transformation that I was talking about. And then 3 times 4 to the e. Well, e looks like a variable because it's a letter, but it's actually a constant. So this is not an exponential. This is a constant function. So this is just like y equals 2, only it's not 2, it's 3 times 4 to the e, but it's just that. Okay, so next example, or this example too, we're going to compute the value without using a calculator. So this is a little bit of review of exponents and how to deal with a fractional exponent. So it says find out what you get when you do x's 1/3. So we're going to write f of x equals -5 times 8 to the 1/3. Of course, we're just going to substitute it. Then we need to remember what 8 to the 1/3 means. So when you have a power, so you're raising something to the fractional power, the top is the power and the bottom is the root. And it's easy to remember that the bottom number is the root because roots of plants are in the ground, so they're on the bottom. So that means we are going to take 8, and it's really the third root of 8 to the first. And we do the root first, okay? Evaluate the root first if you're going to do this by hand. So basically, if it had a root and a power that wasn't a 1, we would do the third root of 8, and then after that, we would do whatever power there is. So here we just finish this. We get -5 times the third root of 8, which is 2. Third root of 8 means what do I multiply by itself 3 times to get 8? And so my final answer here is negative 10. So we'll have to learn how to deal with exponents a lot in this section. Okay, so we want to determine the formula for a function given what you see in this table. So we want to use the values for f and for g both. So it's two different functions. If we plug in the various values of x, we get the certain values for f of x. So we're told they're exponential, so we know they're exponential. So we want to write down the equation that you would get. Well, remember that a is the initial value. So 0 is your initial value. So therefore, a is 3 for f of x. So I'm going to write it kind of under this. So a is 3 for f of x. And then I've got to figure out, okay, what is the base? What am I multiplying by to go term to term? Well, if you look a little higher, it's much easier. 3 to 6 means you're multiplying by 2. 6 to 12 is times 2. And then let's just verify that that's what happens everywhere else. Well, if you take 3/4 times 2 over 1, you definitely get 3/2. Multiply it times 2 over 1, you definitely get 3, and so on. So that means your thing you're multiplying by repeatedly, which is what an exponent does, is 2. So therefore, that means f of x is going to be 3 times 2 to the x. And there you go. So let's look at g. So let's see if we can figure out the pattern here. Again, where you have 0 is going to give you your a. So here a is going to be 5. That's my initial value. And then we're going to look and see what we do to go term to term. Well, here we're multiplying by 1/2 because I have to go in order of left to right with x. And so if we check, we can see that we're still doing that all the way down. We're multiplying by 1/2. So that means that b then is 1/2, because that's what I'm multiplying by. So always think, wait, are you multiplying by? So that means g of x would then be 5 times 1/2 to the x. Now, these would both be examples of something that we call for exponentials, and that's growth and decay. For f, you can see as I go on larger values of x, I'm growing. So this one is called growth. And on g of x, you can see as I go further, this is getting smaller, so we say this is decay. So those are examples of growth and decay. So if we look at what happened there, you can kind of see what's going to happen if I'm multiplying by a number bigger than 1. Like in the case of f, I'm going to keep getting bigger numbers, so it's growing. When I multiply by things between 0 and 1, like 1/2, we get smaller, so that's going to give me decay. So if we look at the combination or the results of that, we see that if we have it's called an exponential growth function if the function's increasing, and we'll talk about growth first and then we'll do decay. So when you have a times b to the x, if you have a is positive and b is greater than 1, then f will be increasing and it's a growth function. And b would be called the growth factor. So you can fill those things in on your notes. And so the example we're going to do is we're going to look at f of x equals 3 times 2 to the x, which is the one we just did. And so we're going to think about all the things that we might look at. And this is why I usually write parentheses instead of dot, but you can do it either way. But it's sometimes that dot gets a little confused there, so I like to write it this way. So we think about things about domain and range and what they look like and things like that. Well, we have some points that we can plot because we just did this problem. So the initial value was 0, 3. So it started here at 3. And then when we had, if we look at some numbers from the table, at 1 we got 6, at 2 we had 12. So we're going to very quickly go up really fast in this direction. And then when we went the other direction, when we plugged in -1, we had 3/2, and -2 gave us 3/4. So at -1, we had 3/2, which is 1.5, so halfway up from what that is, and then down this way for the next one, and so on, and so it's going down this way. So we can see here that the domain would be -infinity to infinity. You can put any number as an exponent. That works just fine. The range, again, usually best to see a graph. Well, there's no possible way for me to get 0 here. So because I have to have 0 times something to get 0, and I've got 2 times stuff, everything being raised. So I'm never going to get 0, and I can't ever get negative because I'm taking a positive number and raising it to powers times a positive number. So my range here is 0 to infinity. Of course, you can see it in the picture too. And then we need to notice that we have a horizontal asymptote here of y equals 0, because the number is going to get closer and closer to 0, but it's never going to get there. It's going to stay right above that. And the horizontal asymptote only exists kind of as you go to the left. So remember that idea of horizontal asymptotes being in behavior. Well, here it only makes sense as I go to -infinity. If I do that for this function, we get 0. That's what that's telling me. So then on contrast to that, we would have a decay function. If we had a positive again and b less than 0, then we're going to get a function that is decreasing, and it's exponential decay. And in that case, then b would be called the decay factor. So let's do this example. We'll do g of x is 5 times 1/2 to the x, which is the other one we made that we had a table for. Well, again, the initial value here was 0.5. So we're going to put a point here at 0.5. And then if we go back to that table and look at some points, we know that when we had -1, we were at 10, and -2, we were at 20. So when we look at our graph, we just think, okay, if I go back a little bit to -1, I'm going to be way up here, and then I'm going to be really high. So we can just kind of see that this is going up really fast over here. And then when I went to the right on some of my points, when I plugged in 1, I had 5/2, and 2, I had 5/4. So 5/2 is 2.5, so I'm about halfway here, and then I'm down, so again, it's going toward 0 again. So this is a decay graph, so it is decreasing and going down. You still have a horizontal asymptote of y equals 0. That hasn't changed. The difference is the direction. Now, if I take the limit as x goes to positive infinity of this function, I will get 0. The reason we get that, if we were to think through this limit, is you're going to take a number that is less than 1, between 0 and 1, and multiply it repeatedly times itself over and over and over again. As I go to infinity, x is going to get bigger. Well, if I keep multiplying something by 1/2, I get smaller, not larger. So this is going to go to 0. And then the domain and range would be exactly the same here. So the domain would be -infinity to infinity, and the range is still 0 to infinity. The graph just comes down and is decreasing instead of increasing. Okay, so now we can describe transformations the same way we do anything else. So if we have the graph of f of x equals 2 to the x is our parent function, then we want to look at what happens if we do 2 to the x plus 1. So first, I'm going to put in just regular black, I'm going to put 2 to the x. Well, a regular exponential function that has never been shifted is always going to go through the point 0a, and in this case 0, 1, because there's a 1 in front. The a here is just 1. So I'm going to go through that, and then its growth, because it's 2 to the x, that means it's going up this way and down this way. So that's your basic exponential graph. Now I made that kind of steep. This one isn't as steep because it's 2 to the x. Let me make it a little bit less. If I do 2 to the x plus 1, well, the plus 1 here is inside the function. And when we add something inside, remember, it moves things horizontally, and it does it sort of backwards. So that means this is shifted or moved 1 to the left. That's how we know how that's shifted. That hasn't changed. So that means that we would take this original point here and we would move it 1 to the left, and then everything else would be moved 1. Now, you can plot as many or as few points as you feel necessary, or I should say, you can plot several points. I wouldn't plot no points because you're going to get not the right shape. So if I want to know better what it looks like, I can simply plug something in. Let's plug in -2. So g of -2, let me do it down here, g of -2 would be 2 times, or 2 to the -1. Raising to a negative power means reciprocal, so we get a half. So at -2, we would be down at a half. And then you can check what you get when you plug in 0. You would be at 2 to the first. And so you're just going to get this graph. It's been shifted 1 to the left. If we do 2 to the -x, again, same original graph. So we have our same original graph here at 1. This is our same original 2 to the x. So we remember that when we do something inside the function, it does stuff horizontally. So it's going to reflect horizontally. Okay, and since it hasn't been moved from the x-axis, this will be over, from the y-axis, this will be over the y-axis. If it had been shifted right or left first, then that would be different. But we're only doing the reflection. So we remember that, again, stuff that's inside the function is going to do stuff horizontally. So it's going to reflect it around the x. So you're going to get the exact same graph, just reflected. So this is now decay again. So another reason to get decay. Well, here's why that's going to happen. If we look at that, you could actually rewrite, so just to notice, 2 to the -x would be the same thing as 2 to the -1 raised to the x. Because remember, when you raise a power to a power, you multiply them. So I can unmultiply them and write it like this. And then if you remember, 2 to the -1 is 1/2. So this is actually equivalent to 1/2 to the x. Okay, so if you get a negative exponent, that's what it's going to do. It's going to reflect it around the y-axis, and growth will become decay, or decay would become growth, depending on the situation. All right, on the next one, the thing that's been done different is this 4 in front, which means that instead of crossing at 0, 1, so my original graph would have been back here again, crossing at 0, 1, you are now going to be crossing at 0, 4, because remember, A is that initial value. So I'm going to get basically the same graph, it's just that it's up at 4 instead. Again, we don't worry as much about the stretches, and you can always plug in numbers, remember? So you can always plot points and see what things look like. Okay, so now we have a definition. So this is a really important definition. It's not something you're going to run around memorizing all the time, and you need that actual definition, but it is super nice when you notice that that's what happens. So the definition of E. So E is an irrational number, like pi. It has no end. It's about 2.7-ish, but that's just an approximation, but it's sometimes helpful if I'm graphing something just so I kind of have an idea about what it equals. So if you were to look at the function on your calculator, 1 plus 1 over x, that whole thing raised to the x, and you were to go way to the right, put in really big numbers for x, you would see that it will begin to flatten out and look like a horizontal line at y equals e. At about 2.7 something, you're going to see it flatten out. So this is actually the definition of E. It's this limit. You may have studied it before when you did growth and decay with interest rates and so on, okay, in Algebra 2. So we can rewrite any exponential function like this if we get the appropriate value for k, then any regular exponential function, so this function can be rewritten like that if we can find the right value of k. So this is typically what we use when we talk about exponential growth and decay. So when you hear somebody says this thing's growing exponentially, it has exponential growth, we normally are looking to fill in this model, a times e to the kx. In this case, if a is positive and k is positive, it's growth. If a is positive but k is negative, it will be decay. So you're going to need to have some sort of conditions in order to figure out what k is. So generally we have a situation that we know something grows exponentially and here's this value, and so here's one situation that works, and so you can solve for k. All right. So we're going to talk about e to the x as a graph. So remember, e is about 2.7 something, 2.71828, but you know, so to actually plot points would be difficult here, but you could do it by, like, to graph e to the x, but we certainly know that it crosses at 0, 1, because that's where all exponentials cross. If they don't, if the a is 1, they cross at a, and here a is 1. And then we could guesstimate when x is 1, you're going to get e to the first. Well, we just said e is about 2.7, so that means this point would be about right here. So that would give me at least an idea of about what this exponential graph, the steepness of it. So you can always, I suggest you always put the initial point on the y-axis for an exponential and graph at least one to the right. Once you get the curve to the right or left, whichever way is growing, I guess, is going up, you can get a pretty good idea. Now this one is going to end up having the -2 part. Remember, we don't do much with the stretching, but the negative part is what we're more interested in. So the negative part is going to make sure it's reflected. And then the 2 to the x is just going to change the steepness of it, which again, I would just plot some points. But the main thing is to recognize the negative makes this reflected about the y-axis. And then the 2 changes the steepness of it, which you can just plot some points to figure that out. On your calculator, you have a button for e, and make sure you use the e to the x button to do something. So for example, if I want e to the first, I have to use the e to the x button and put e to the first. You cannot use the letter e on your calculator. We'll do much more calculator stuff in class. All right, so now we're going to talk about logistic growth, and then we will actually do these examples, or most the rest of this probably in class. So we're going to talk about logistic growth a little bit, and then we'll actually cover that example in class as a kind of a review for all of this. So logistic growth is written either way. More often you're going to deal with it like this. Definitely in calculus you will deal with it written in this format. So we're going to talk about that format more. It's called a logistic growth function, and there's some interesting facts about those different values. And C is really important. C is the limit to growth, or we also call it the carrying capacity. And so what that means is that this is typically very often like a population growth, and it's saying that's the most growth that this particular population or whatever situation can handle. So for example, if we were talking about the spread of a virus through a school, for example, well, if there were 1,000 students at the school or 1,000 people at the school, then C in this case would be 1,000, because that would be the most people that could get this virus because there aren't any others. Or if we were putting bacteria and growing them in a petri dish, then the carrying capacity is whatever fits there. If it's different things, that's going to be the carrying capacity. And the reason it works out that way is if we take the limit of this, and we'll do more of this in calculus, but if we go to infinity, so we let x be really, 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 really big as we can possibly get it, you're going to take a really, 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 really big number times a negative, which makes it a really, 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 really small number. So you're going to have like e to the negative a million. Well, remember that e to the minus x actually means 1 over e to the x. That's the definition of a negative exponent. Well, 1 over a really, really, really big number is really, 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 really small. So essentially this thing will end up going to 0. And so 1 plus 0 is 1, and so you'll get the carrying capacity. So that's kind of how that works. We'll do more examples. We'll do one of these examples, and then we'll do the other in class. So if I want to graph this function, well, it's just like anything else. I have to figure out some things to see what's going on here. So y-intercept. Y-intercepts are always set x equal to 0. So you would have 18 over 1 plus 5 times 0.2 to the 0. Well, if you raise a number to the 0, anything raised to the 0 is 1 except 0 to the 0. So you're going to end up with this thing equaling 1. So this is going to be a 1. And so you're going to have 18 over 1 plus 5, which is 18 over 6, which is 3. So that means that the y-intercept here is at 0, 3. That's the y-intercept. Now, we got to think about horizontal asymptotes. So let's look at this graph carefully. You will notice that you have 0.2 being raised to a power. That's a positive number raised to a power, and it's not 0. So there's no possible way for me to get a negative number here, and there's no possible way for me to get 0. So I'm going to have a horizontal asymptote right on the x-axis. The other asymptote is that whole idea of the carrying capacity. As I go to infinity, well, if you take 0.2 to a really, really, really big number, remember 0.2 times 0.2 times 0.2 times 0.2 gets smaller because it's a number between 0 and 1. So this is going to be super small as I go to infinity. Times 5, still super small. So effectively that bottom is, this part is going to 0. So the other asymptote I'm going to have is 18. Now, even if you don't understand that idea of that limit, then you can just remember that this is going to be the carrying capacity, or the largest value that you can have. Then what this graph will look like is it will be coming up and growing here, and then it will be growing still, but it has kind of a limiting factor, so it sort of slows down growing. So we'll do the last example in class as a way to review everything that we've talked about. So this is your final part of the notes for now.